Okay, this lecture is mostly about ionic compounds, formulas, names, and properties. Now, we've actually covered the properties before. We covered them with the molecular compounds or covalent compounds because it's nice to contrast the list, to compare them, that is. So the goals here are to recognize that metal atoms commonly lose one or more electrons to form positive ions. They're called cations. And nonmetal atoms often gain electrons to form negative ions called anions. Predict a charge on monatomic cations and anions based on group number. Write formulas for ionic compounds by combining ions in a proper ratio to give no overall charge. Give the names and formulas of ions and ionic compounds, and understand the importance of Coulomb's law in chemistry, which describes the electrostatic forces of attraction and repulsion of ions. So it seems like there's a lot here, and there actually is. So let's go ahead and get started. So let me zoom out a bit so we can see all of this. So we're looking at ionic compounds, formula, names, and properties. Let's start first with ions. An ion is a charged particle on an atomic level. There are two types of ions, something called a cation and something called an anion. Don't ever let me hear you saying cation, because that's not what this is. It's cation. Cations have a positive charge, which means that the number of protons is greater than the number of electrons. And the charge tells you how many more protons there are. So if we look at this, this is a common cation, the sodium cation. It has a charge of +1, so therefore there's one more proton than there are electrons. And we know how many protons there are in sodium because we can look at the periodic table. There it is. The number at the top, 11, tells you how many protons. So the sodium ion has 10 electrons. Same for magnesium. This is a very common ion. That's a cation, the magnesium ion. It has 2 more protons than it does have electrons. So if we take a look at magnesium, the number up here is 12. So it has 12 protons in the nucleus. And for it to be a +2 charge, we're going to have to lose 2 electrons. And therefore, with 12 protons, it's only got 10 electrons. Now you might ask, well, why don't we just lose protons or add protons to it? Well, if magnesium has 12 protons, and to make this positively charged, we add 2 more protons, we don't have magnesium anymore. What do we have? We have silicon. So it's important for you to know that atoms of elements become ions by either losing electrons or gaining them. Cations lose them. Anions gain them. What's them? Electrons. Okay. Anions have a negative charge, and that means the number of electrons is greater than the number of protons. And here are 2 examples of anions. This is called the fluoride ion, and this is called the oxide ion. You'll notice the names here end with "ide," whereas up here, the names sound like the element, but we say ion to let people know that it is the ion. When I write the symbol of an element with the charge, I usually circle the charge so that you know it's a charge and not raised to the 2nd power or something like that. So this is cation formation. So here's my proton and here's my electron. Since this has 1 proton, it's a hydrogen atom. To show that this is losing an electron, here's the proton with the where it's lost an electron. Where's the electron? It's over here. So we're observing what's called the law of the conservation of matter. So we're counting for the same amount of matter on both sides of the arrow. And symbolically, how do we write it? We write it this way. So here, the neutral hydrogen atom has become a charged hydrogen ion plus an electron which has flown away. Well, where has that electron gone? Well, maybe it's gone to another atom. So this is anion formation. So here I have 7 protons and 7 neutrons and 7 electrons. Remember, neutrons have no charge. Protons have a +1 charge. Electrons have a -1 charge. Now, the total amount of charge in the nucleus is +7. The total amount of charge outside the nucleus is -7, which adds up to 0, a neutral atom. And here it is. With 7 protons, we're talking about a nitrogen atom. So maybe 3 hydrogen atoms gave up electrons and they all came to this nitrogen atom. And here's how we signify that this is gaining 3 electrons. So there's the 3 electrons, and then it becomes, well, notice the nucleus doesn't change. It's the same nucleus, same size. But notice that the electron cloud becomes larger. When you add electrons, the cloud becomes larger. When you take them away, it becomes smaller. So this anion now has 3 more electrons than protons, and therefore it has a -3 charge. And this is how we write it symbolically. So you should also notice that this is a nonmetal, and usually nonmetals become anions, metals become cations. So if we go back here, we can do another example with a metal, and I'll make it a little smaller. So we're going to take a look at a sodium. We're going to look at a sodium, so 11 protons and 12 neutrons. So there's the nucleus. And then we have 11 electrons. And then what we're going to do here, 11 protons and 12 neutrons. And I'm going to make this smaller because we've lost an electron. And where is that electron? There it is. So the way we would write this is sodium is becoming a sodium ion plus an electron. So we say here that this sodium is about to lose an electron, or this sodium loses an electron. So that's cation formation, and that's anion formation. Let's take a look at the monatomic ions. So these are ions made out of single atoms, okay? So they are almost always going to be nonmetal elements. And here we're going to look first at the monatomic anions, and these are the nonmetals, okay? You want to memorize the name of each one of these and the charge on each one of these. Now, what's nice about the charge is if you know what group it's in, it's always the same charge. -4, -3, -2, -1. If I were to put neon in here, the charge would be 0. So of course I don't have a name for that ion because it's not an ion. Now this is like the periodic table where this is group 8A, 7A, 6A, 5A, and 4A. So how can we remember these charges based on the group? Well, if you can remember that group 8A is 0, and this is basically a number line going in the negative direction, it's 0, -1, -2, -3, -4. You need to memorize those charges. You also need to memorize the names. I call these names elemide. It's the name of the element plus "ide" at the end. You take off a portion of the element name. So we have, respectively, fluoride, chloride, bromide, iodide, oxide, sulfide, selenide, nitride, phosphide, and carbide. So memorize those anions. Now let's look at monatomic cations. These are going to be metal ions. Now this comes after the anions because it's a little more complex. We have 2 types of monatomic cations, those that are fixed charge and those that are variable charge. Fixed charge means it doesn't matter what compound it's in, it's always going to be the same charge. Variable charge means that the charge on the ion depends on the compound. So an example of fixed charged ion is sodium ion. It's always a +1 regardless of the compound it's in. An example of a variable charge is iron. There are 2 iron ions that are commonly found in compounds. One is called iron 2 and one's called iron 3. And the charge is written in Roman numerals behind the name of the element. So again, with the +2, it's called iron 2 ion. With the +3, it's called iron 3 ion. That is the standardized way of naming the variable charge metal cations. Okay, let's look at those fixed charge cations. These are the ones you need to memorize. In group 1A, they're always a +1. In group 2A, they're always a +2. In group 3A, they're a +3. I don't have a complete list of the group 3A because we don't run into those elements down here very often. There are some others, and they are silver and zinc. Zinc is always a +2, silver is always a +1. So if we take a look at the names of these, this is lithium ion, sodium ion, potassium ion, rubidium ion, and cesium ion. We have to use the term ion because if we say lithium, that's a neutral atom of lithium. Lithium ion is the cation. So, how are you to remember the charges here? It's easier than the anions because the charge is the same as the group number. 1A +1, 2A +2, 3A +3. Now, silver and zinc are not main group elements. They're not in the A groups. How are you going to memorize those? This is how I remember them. It's like a staircase of elements. Aluminum is covered by group 3A, but silver, zinc, and aluminum make a nice staircase of elements where I can remember aluminum's a 3, therefore zinc, lower on the staircase, is 2, and therefore silver, lowest on the staircase, is 1. So this is called silver ion, and this is called zinc ion. So when I say zinc ion, you're supposed to be thinking +2 charge, boom, immediately. Here's another one where you want to pause it after I talk about it, so you can write these notes down. There are cations of variable charge. There's no need to memorize these variable charges because the name will tell you the charge, or you can figure out the charge from the formula. So these are examples of the standardized names in this first column here. Fe2 is iron 2 ion, Fe3+ is iron 3 ion, Cu1 is copper 1 ion, Cu2 is copper 2 ion, and so forth and so on. Now, it does help you to remember some of these common names. So Fe2+ is ferrous and Fe3+ is ferric. And you'll always find that the ferric, or the ic, has a larger positive charge than the us. But it's not always 2 and 3. If you look at copper 1 and copper 2, it's cuprous and cupric. So 1 and 2 is the difference there. And so you might think, well, if you know the us, you can figure out the ic because it's 1 different. And the answer is no. There is stan us, which is a +2, and stan ic, which is a +4. So it really doesn't help to know all the us's to figure out the ics. You just got to memorize them. But we don't have to. We're not going to. And here's a little play on words here. If you take a look here, this is supposed to represent something. So what do I have there? I have these iron 2 ions on that thing that looks like a wheel, a Ferris wheel. Okay, there we go. Stupid joke number 1 today. Now there are also polyatomic ions. So a monatomic ion is an ion made of a single atom. A polyatomic ion is an ion made of multiple atoms. This is an example of a polyatomic ion. It has 1, 2, 3, 4 atoms in it. The atoms are covalently bonded together. Okay? And so that means those atoms are bonded together. This whole large thing is an ion. Now, what this means is that simply that it's partially molecular, but because it's an ionic compound, it's ionic. Okay. Now, if we take a look at this, we can actually figure out how many electrons it has. And here's how you do it. This has 31 protons, 3 oxygens at 8 apiece, which is 24, 1 nitrogen at 7 apiece. 7 and 24 is 31. It has 31 protons. Now, since it has a negative charge, it will have more electrons. And remember, we can't change the number of protons. We can only change the number of electrons. So if it has 31 protons and has to have a -1 charge, how many electrons does it have? 32. Okay. Now, let's take a look here. And we're going to take a look at those monatomic. Let's take a look at some of these monatomic if you will, anions. So nitrite is a -3, and oxide is a -2. Is that supposed to be a -3, a -2, a -2, and a -2? Well, let's think about that for just a moment. What do we say about charges? There are two properties. One, opposites attract and like repel. That's one property. And the other is charges are additive. So if that's a -3, that's a -2, that's a -2, that's a -2, what does the charge add up to? And does that charge equal what we know about it? Something to think about. Now, here are some polyatomic ions to memorize. You'll notice that all of them are anions except for one. The one cation is the ammonium cation with a +1 charge. We've got the hydroxide with a -1 charge, the acetate with a -1 charge, the nitrate with a -1 charge, and the chlorate with a -1 charge. Sulfate has a -2, carbonate -2, and phosphate -3. You probably want to memorize these. Now, for the exam, you do get a 3" by 5" card of information, but this shouldn't be on there. This is something you should know because you're going to need it not only for exam 1, you'll need it for exam 2, exam 3, exam 4, and so forth. So you should memorize that information. Next, we have variations on these polyatomic ions. I call this the H+ variation and the 8 variation, if you will. Okay, so here, the phosphate ion is PO4 3-. If you add an H+ to this, +1, the +1 and the -3 add up to -2, so that explains the charge here, and get HPO4, and this is called the hydrogen phosphate ion, okay? Now, what's happening here is you have an H+ combining with a PO4, so here's the PO4 3-. Notice the 3 negatives here. And what happens is the hydrogen bonds to one of those oxygens, essentially neutralizing that oxygen, +1, -1, neutral. So now you end up with an ion with a -2 charge, and you don't end up with two pieces. So this is really interesting. Two ions combining together to make one big ion, okay? So that's how you make the hydrogen phosphate ion. I bet you can guess for this one called dihydrogen phosphate where the next hydrogen is going to go, right? Either here or here, your choice. I'd put it here because it'd make it look more symmetrical. And then where would the third hydrogen go? It would go on the remaining oxygen, and you'd end up with something neutral. So these names are called phosphate ion, hydrogen phosphate ion, dihydrogen phosphate ion, di for 2 hydrogens, and then finally, when it's neutral, it's called phosphoric acid. Now here's the 8 and 8 variation. Chlorate is one that we had on the previous page. Now this variation is always the same. What I mean by that is that the two elements will be the same, but the number of oxygens will be different. The charge is always the same. So -1, -1, -1, -1, and chlorine and oxygen. Now here's the 8, ClO3 -1. The 8 has one less oxygen, so ClO2 -1. What if you had one less oxygen again? Well, it'd be ClO -1. Now, how do we call that? Well, because it's lower than chlorite, we call it hypochlorite. You've probably heard of hyperactive. Well, that's a kid bouncing off the wall all the time. Hypoactive means a kid who sleeps all the time. So we're talking teenager. All right. So what happens if you have one more oxygen, ClO4 -1? Well, naturally, that seems like it should be hyperchlorate. But the high, you can see I've made it very faint, is not in the name. It's simply called perchlorate. And I think the reason why is because hyperchlorate sounds a lot too similar to hypochlorite, and they're trying to distinguish between the two. So you should know both variations. Let's take a look at some problems here. Ionic compound formulas. For each of the following ionic compounds, write symbols for the ions present and give the relative numbers of each. So we know that we have 2 lithium ions, plus we have the carbonate ion. So we want to be able to recognize this as a polyatomic ion. Now, where do we get the charge on the lithium ions? And the answer is, well, here it's right there in group 1A, so they're both +1s. Where do we get the charge for the carbonate? Well, we can get it 2 ways. The best way is you memorized it. But what's another way to figure out what the charge is? Well, the answer is all of these charges have to add up to 0. So +1, +1, and question mark has to equal 0. So what's the answer there for the question mark? And the answer is -2. So overall, we're going to have a lithium plus a lithium plus a carbonate, which is equal to 2 lithiums plus a carbonate. So these are the relative numbers of each, 2 and 1. If we don't write a number in front of it, it's assumed to be a 1. All right, let's take a look at this next one. What are the ions? Well, remember, the metal ions are the ones that form the cations, and there are 2 irons. Iron is a variable charge one because it's not in group 1A, 2A, or 3A, and it's not silver, and it's not zinc. So we have to figure out what the charge is on this iron. So I'm going to put X here for the charge. Plus we have a sulfate, and a sulfate. So here, since we don't know what the charge is on the irons, we better darn well know what it is on the sulfate. Now, you just learned it, so if you don't remember it by now, that's okay. You will memorize it. It's a -2. Now, I'm going to show you another way to kind of tackle this. Can you see that the total amount of charge here for the sulfate is -6? So what does the total charge here on the iron have to be so this thing ends up being neutral? And the answer is +6. So it looks like I've got a formula here that says 2x is equal to 6, which means x is equal to 3. So that means that we have 2 iron 3 ions plus 3 sulfate ions. And that is the charge of each ion and how many of each. This thing here, where we write the formula of the ion with its charge, that's called the formula of the ion. Okay. Next, ionic compound formulas. Write formulas for ionic compounds composed of an aluminum cation and each of the following ions. So, fluoride ion and an aluminum cation. What I'm going to do to help me out is I'm going to write the formula of an aluminum cation. I know it's +3. And I'm going to write the formula of a fluoride ion. So it's -1. Now, the best way to get the formulas for these is to do what I call a switch and simplify. Switch and simplify means that you take the charge of one ion and make it the number of the other ion. So the fluorine ion has a charge of 1, so we're going to have 1 aluminum ion. And since the charge on the aluminum is a 3, we're going to have 3 fluoride ions. So can you see here we've got +3 charge, and here we've got -3 charge, which should give us a neutral compound. So if I know I need 1 aluminum and 3 fluorides, how do I write that out? You always write the cation first, the anion second, and then you put how many of each after the symbol. If there's 1, you don't write anything. That's default. So this is the compound formed from an aluminum cation and fluoride ions, AlF3. So we can simplify this quite a bit. So I'm going to write Al3 plus and sulfide 2 minus. How do I know sulfide's a 2 minus? Well, remember the periodic table, 0, -1, -2, -3, -4. So sulfur is 0, -1, -2. Sulfur is going to be a -2. So the switch and simplify says that Al will have a subscript of 2 because the charge on sulfur is 2. And the sulfide will have a subscript of 3 because the charge on aluminum is 3. So we haven't seen the simplify part yet, but again, I keep saying switch and simplify. So this is the switch. Let's look at this one here. We have an aluminum ion and a nitrate ion. So that means we're going to say 1 aluminum and 3 nitrates. So how does that look? 3 nitrates. It looks like 33 oxygens to me, so it's wrong. So how do we indicate 3 nitrates instead of 33 oxygens? Well, if you have more than one of the polyatomic ion, you put a parenthesis around it. So there you go. Let's look at another one. So we're going to call this D. We're going to look at the aluminum cation and the nitride ion. Now, nitride and nitrate sound a lot alike, but remember that term I gave you, elemide, means an element, right? So nitride is N3 minus. So this 3 becomes aluminum 3, and this 3 becomes nitrogen 3. But we want the simplest ratio. What's the same as a 3-to-3 ratio? And the answer is 1-to-1. So this is the simplify. Switch, simplify. Now, can a 1-to-3 ratio be simplified? Nope. 2-to-3? Nope. 1-to-3? Nope. And let's do one more example where we don't use parentheses here. Let's do aluminum phosphate, E, phosphate. So we have aluminum, 3 plus, phosphate, 3 minus. So that would become Al3, phosphate, 3. Now, when we have these parentheses, that means 3 of those ions, and we're simplifying the numbers of ions. So we can simplify this to AlPO4, and we don't use the parentheses around PO4. Okay. So here we have some notes that cover basically all that stuff that we had done. Formulas of ionic compounds, they're neutral, simplest ratio, cation first, anion second, do not show charges, and you do the switch and simplify. Switch and simplify says the charge on the cation is the number of anions, and the charge on the anion is the number of cations. So here are some more examples, including the ones that we've done already. If you have a sodium ion and a chloride ion, do the little switch and simplify, you get sodium chloride. Sodium ion and sulfide ion, elamide, sulfide. So we have 2 of these guys because of that, and we have 1 of these guys because of that. So Na2S, and there you go. SN4, tin 4, and oxide ion. Since the oxide has a 2 charge, you have 2 tin 4s. And since the tin 4 has a 4 charge, you have 4 oxides, which becomes SN2O4, simplifies to SN12 or SNO2. And here's some more examples with polyatomics. So we have the ammonium ion and the hydroxide ion. You need 1 of each. So here, that's what it would look like with parentheses, but since there's only 1 of each, we don't need the parentheses. Here's the ammonium ion and the carbonate ion. Because the carbonate's a 2, we need 2 ammoniums. Because the ammonium's a 1, we need 1 carbonate. I'm going to make this look like a 1 by putting a little like that, so it's clearly a 1. So how do we write this? Well, 2 ammoniums, 1 carbonate, And we get rid of the parentheses on the carbonate. Don't leave it like this, it's wrong. This is correct. And here's aluminum ion and sulfate. Okay, names of ionic compounds. So the names of ionic compounds is simply the name of the cation and the name of the anion. But you don't put ion into the name of the ionic compound. So here's an example. If you have sodium ion and chloride ion, the name of the compound is sodium chloride. How are we supposed to know that's an ionic compound if we don't put ion in there? And the answer is simple. Sodium's a metal atom. Chlorine is a nonmetal. Metal, nonmetal, ionic. Okay, here's an ammonium ion and a sulfide ion. Or excuse me, I said ammonium. Sodium ion, and a sulfide ion, sodium sulfide. Here's a tin 4 ion. Here's an oxide ion, tin 4 oxide. Why do I have to use the Roman numeral with tin? And the answer is because it's not in group 1A, it's not in group 2A, it's not in group 3A, and it's not silver, and it's not zinc. The list of those where you don't have to use a charge is smaller than the list of those that you have to use a charge. So I remember the list of those where you don't have to write the charge. All others, you write the charge. So here's the formula and here's the name. Likewise, we have similar names. Do you see any prefixes in these names? The answer is no. You rarely see a prefix in the name of an ionic compound, but you do see them in binary molecular compounds. Okay, and I believe this is the last little thing we're going to talk about, the strength of ionic bonds. So this is basically Coulomb's law. So this is the force of attraction of an ionic bond, okay? Now, if this were a positive value, the force would be a repulsive force. A negative value means it's an attractive force, so that's why the negative is in there. The E is the charge on an electron, which is a negative charge. So a negative times a negative ends up being a positive. N is the number of, what is it? N is the size of the positive charge, and N is the size of the negative charge without regard to charge. So if your positive charge is 3, N is 3. If your negative charge is -2, N minus is 2, okay? D is the distance between the nuclei of the ions. So if we tear this apart, we can see that the force is proportional to the positive charge. The force is proportional to the negative charge. The force is proportional to 1 over the distance between the nuclei squared. The force is attractive because it's negative, okay? So we call it a force of attraction. And this is something that you want to know about Coulomb's law. So how do we use this? And the answer is pretty simple. If you have ions that have larger charges, they will stick together better, harder to melt. If you have ions with smaller charges, they stick together less well, easier to melt. So when we talk about ionic compounds, they have high melting points and high boiling points. But which ones have the lower of the high melting points? And the answer is, well, the ones that have smaller charges. But also, distance matters. The bigger the distance, since this is in the denominator, that means the smaller the force. So big ions aren't as attracted to one another as small ions are. So small ions are more attracted than big ions, okay? So that means that if you have a compound made out of 2 really large ions, it's going to melt easier than a compound made out of 2 small ions if all charges are equal. So we're going to do a quick comparison of these 2 ionic bonds, sodium chloride and magnesium sulfide. And we want to kind of figure out, well, which one has a higher melting point if we had to guess. Well, sodium is a sodium plus 1 ion because it's in group 1A. Magnesium is a plus 2 ion because it's in group 2A. Now, since these ions are in the same period, that means their diameters will be very similar in diameter or length. Now, the chloride ion is a Cl -1 because it's in 7A. Sulfur is a -2 because it's in 6A. And remember, for those anions, we start with the noble gases and go 0, then -1, -2, -3. Okay. So here, the magnesium ion, similar in size to the sodium ion. Sulfide ion, similar in size to the chloride ion. So which of these has a stronger force of attraction? Well, since the distance between the nuclei is about the same, that goes out the window. But here, the charges are different. Here, the charges are 1 and 1. 1 times 1 is 1. Here, the charges are 2 and 2. 2 times 2 is 4. So this is, if you will, 1/4 the attractive force compared to this one. Or you could say that this is 4 times greater. So you could write it either way. So if this has an attractive force that's 4 times greater than the sodium chloride, that means this will have the higher melting point. Okay, so just kind of a little test here. What are the names of these compounds? I'll tell you, one of them is copper 1 oxide and the other is copper 2 oxide. So what you want to do right now is you want to hit pause, figure out the formula of each ion, figure out the name of each ion, and then put it together. So you're going to start off here, CuO and Cu2O. You're going to get the ions, you're going to get the ion names, and then you get the name of the compound. So you're set up to succeed if you know what you're doing, but you may not. So let's give it a shot. Hit pause. After you've worked it out, hit play. Oh, no. You don't hit play again until you've done the work. Hit pause. No. You have to hit pause. You don't just get to see what's going to happen without hitting pause. That's better. Now let's take a look at the answer here. So for this one, we've got 1 copper. I'm going to put an X here. And we've got 1 oxygen. I'm going to put a Y here. We know that the copper is going to be, or the oxygen is going to be a -2 because of where it is on the periodic table. And therefore, the copper has to be a +2. All right? So what is the name of this ion? It's called copper 2 ion. What's the name of this ion? It's called the oxide ion. We put the two together and we get copper 2 oxide. Interesting, there's no 2 in the formula, but it's called copper 2 oxide. What's the 2 all about? It's the charge on the copper, not how many. So over here, we've got a copper, and an oxygen. The oxygen's fixed at a -2. What does each copper have to be to make this work? +1. So we've got copper 1 ions, and we've got the oxide ion, and we write out copper 1 oxide. Even though there's 2 coppers, we don't write di, we just say copper 1 oxide. So that kind of begs the question, if we had copper 1 oxide, would we get Cu2O? Well, let's find out. So here's the name, copper 1 oxide. Let's see if we get the correct formula, which we already know is Cu2O. Well, this is a copper +1. This is an oxygen -2. Do the switch, Cu2O1, and boom, yeah, we get the right formula. We don't need to know there's 2 coppers from the name. We get the 2 coppers because it's implied when you figure out the formula. Okay, that's the end of this lecture. Thank you for listening.